So now we want to make the connection with thermodynamics. Although the first connection that we made with thermodynamics was with the expression minus Kb sum over Pj ln Pj as the entropy, because this has all the properties of the entropy that we encountered in thermodynamics. It's an additive quantity, which means it's an extensive quantity. It's a monotonic function, so everything is satisfied just as we had seen in thermodynamics, right? Now, the first law of thermodynamics is the zeroth law, and we have seen what the zeroth law essentially tells you, that it brings in the concept of a temperature, right? So let's bring two microcanonical systems together. So that one of them have the energy E1 and the other one has the energy E2. When you bring these two together, the total energy becomes E1 plus E2, right? And you know the interaction between the parts, so that the microstates becomes x1n outer product x2n, okay? Your density rho of xn is 1 over omega times E, where omega of E is now has to be carefully defined, is essentially integral d of xn delta of hn xn minus E. And the Hamiltonian, given these two energies, the Hamiltonian of the system is, combined system is x1n plus hn x2n. Correct? So this becomes, so let us rewrite this carefully. This is dx1n dx2n delta of hn xn minus E, right? Good. So now let us recast this equation as dx1n dx2n delta of hn xn minus E delta of h1n xn minus E1. These two, the left and the right hand sides, are identical. There is no difference in that, right? But the moment you bring this, one also has to write down this carefully. The moment you introduce this, I can equivalently delta of h2n xn minus E plus E1 delta of h1n x1n minus E1. So the integral over E1 will bring in the using the delta function. If you know integrate over E1, this E1 is going to be replaced by this. So this clearly tells you that this is dx1n delta of h1 x1n minus E1 dx2n delta of h2n xn x2n minus E minus E1. And you quickly identify this to be dE1 omega E1 times omega E minus E1, right? So you bring two microcanonical systems together. Each had energy, one had energy E1 and then one had energy E2, and then you bring them together. So this is the total number of microstates for the joint system. So omega E is integral dE1. This has to be omega 1 E1, this has to be omega 2 E minus E1, right? But omega 1 E1 from the definition of entropy is S over Kb. So this is S1 E1 over Kb plus S2 E minus E1 over Kb. Correct? Now, entropy is an extensive quantity. Right? So therefore, since this would mean that S1 is proportional to N1 and S2 is proportional to N2, with the understanding that both N1 and N2 are very large. Consequently, with this, since this term scales with N1, this term scales with N2, this argument of the exponential is very, very large. And I can evaluate this integral using a saddle point method at the extremum point of this expression. And suppose I do that, and this gives me two energies, E1 star and E2 star, which means what is being said here is that if once I bring the two systems, microcanonical systems, together, they find a joint equilibrium by extremizing this quantity. Correct? How will you extremize? Well, del S1 del E1 plus del S2 del E1 is equal to 0. Right? So which means del S1 del E1 plus del S2 del E2 del E2 del E1 is equal to 0. This is the saddle point you are trying to determine E1 and E2 star. But E1 plus E2 is the total energy E, and therefore del E2 del E1 is equal to 1 plus del E2 del E1 is 0, which means del E2 del E1 is minus 1. And therefore, you have del S1 del E1 at E1 star is equal to del S2 del E2 at E2 star. This effectively tells you that when the two microcanonical systems are being brought together and they go into a joint equilibrium, and that joint equilibrium happens by extremizing this expression, the entropy, which gives you E1 star, E2 star, and this condition is satisfied. And this, from thermodynamics, we know that is the inverse of the temperature. So the joint equilibrium, when they come to a joint equilibrium, there is a thermodynamic property which becomes equal for both of them. And this is essentially the sense of the zeroth law, that if A and B are brought together, B and C are brought together, then are in equilibrium, then A and C also are in equilibrium. So therefore we see that essence of the, as we saw in the thermodynamics, that the essence of the zeroth law was that it tells you that there is a common thermodynamic state function when all the systems are in joint equilibrium, and this is exactly also what we find out. So we bring the two microcanonical systems together, bring them to a joint equilibrium, and we see that these two derivatives must be equal at the joint equilibrium at these energies E1 and E2 star. And these two are essentially 1 by is the inverse of the temperature. Further, note that since we have evaluated this integral that we have written down over here using the saddle point, our omega E omega E is approximately e to the power s of E1 star over kb plus s of E2 star over kb, so that the entropy of the total system is approximately s of E1 star plus s of E2 star. This expression can be derived, you can arrive at this expression if you just take a log of this equation. Now, the above definition of equilibrium, of joint equilibrium, essentially rests on the fact that there is a large degrees of freedom and much larger than 1, that makes it exponentially unlikely that the component energies of the system is anything other than E1 and E2 star, which effectively means that the equilibrium point is such that a larger number of accessible states have the energies E1 star and E2 star than any other energies. So essentially, one can write down E1 star comma x1. So I'm replacing the generalized coordinates, the v and the n, by x1 by the generalized coordinates x. Much larger than omega E1 x1 . We have to be careful with the notation. So omega 1, omega 2. Now this effectively means that delta S is S1 E1 star plus S2 E2 star. Well, the x1 is also there, comma x1 comma x2 minus S1 E1 x1 minus S2 E2 x2 is greater than equal to 0. This expression you arrive at by taking a log of this above equation. Therefore, you have delta S is greater than equal to 0, so that there is an irreversible flow of energy. Now I can write down delta S. When the two microcanonical systems were brought together without any work being done, then I can write down, then the equilibrium condition T1 equal to T2 equal to T is not satisfied, and therefore my delta S is del S E1 minus del S2 E2 times delta E1 is greater than 0. And this essentially means that 1 by T1 minus 1 by T2 delta E1 is greater than equal to 0. That essentially tells you that the heat flows from a hotter to a colder body, which is your Clausius's theorem. Now finally, we want to allow a variation in S of E, x by changing the coordinates from x to x plus delta x, so that the work done d cut w is f dot delta x. This is the generalized force, as you are well aware of the description, the language that we used when we did thermodynamics, right? In which case your delta S is S of E plus F dot delta x, x plus delta x minus S of E comma x. So this is equal to del S del E F dot delta x, because this amount of work changes the energy from E to E plus F dot delta x, right? Plus del s del x, which is del s del e f plus del s del x dotted with delta x, which we have just now seen that del s del e is equal to 1 by t is f by t plus del s del x dot, right? Now therefore, look at this expression of delta s. A spontaneous change is going to occur if this expression in the bracket is non-zero, right? So in order that you are at equilibrium, therefore there is no spontaneous change, delta s is 0, would mean that fi over t minus is del s del x psi, with e and xj being held constant. So we have now identified the derivatives of s. Del s del e at x held was 1 over t, which we saw in the zeroth law, and this is the one we see that if we allow any variation in the coordinates, then my delta s is going to be like this, but since it's an equilibrium, it's a joint equilibrium, the delta s has to be 0, otherwise you are allowing a spontaneous change. And therefore your ds is, since you know the variations in e, this is de by t minus f dot dx by t, and you arrive at the first law, which tells you that tds is de minus f dot dx, right? So in summary, we started off with a probability density which we said was 1 over omega e comma x, where this we said is the number of microstates, the total number of microstates and using this definition of rho, using this expression for rho, we constructed the entropy as minus kb dxn rho xn ln rho xn divided by cn, so that substituting for this becomes kb ln omega e comma x divided by cn. And we further showed that the connection, this is really the entropy that we worked with, or that we can link with the entropy that we had defined in thermodynamics. In thermodynamics, we have defined just the entropy as a state function, which was a function of uvn, or s as a function of u comma x. We see that these two have a very nice correspondence. They not only have the properties that is satisfied by entropy, but if we build in, if we start looking at the laws of thermodynamics, then indeed this expression for entropy satisfies, gives me all the laws of thermodynamics. It gives me the zeroth law, it gives me the first law, it gives me the second law, right? So therefore, starting from a microscopic picture where we were initially interested in the microstates of the system Xn, we have built something which is very much consistent with thermodynamics that we did earlier. The connection, of course, comes in from this probability density that takes you to the entropy. Expression for the entropy, ln omega e comma x divided by cn, right? So there is one thing that I should point it out, and I should note that while we considered the derivation of the zeroth law, when we brought the two microcanonical systems together, we only allowed an exchange of energy. We did not allow any exchange of work. There was no exchange of work. This we did later on when we derived the first law of this, when we changed the coordinate so that over here when we change the coordinate from x plus delta x, so that the energy now changes from E to E plus F dot delta x. This you should keep it in mind.